Understanding how shock propagation travels through interstellar comet nuclei offers critical insight into their internal structure and resilience. By comparing the pre- and post-collision gas compositions, scientists can identify changes in volatile layering, revealing how these ancient objects are stratified. If the impact exposed deeper layers rich in previously hidden gases, it could mean that 3I Atlas contained reservoirs of exotic volatiles trapped beneath insulating crusts. The collision may have released organics, rare isotopes, or uncommon gas species that were dormant before. Clues that help reconstruct the comet's thermal evolution, formation history, and original environment. Moreover, the very occurrence of the collision implies the presence of dust, microrocks, and debris along its trajectory, suggesting that interstellar space, once thought empty, is in fact seeded with remnants from past collisions or ancient debris disks. This raises profound questions about how frequently such impacts occur during interstellar transit and how many objects are altered or destroyed before ever reaching another star system. The timing of the collision is especially significant. 3I Atlas was nearing perihelion, already under thermal stress from solar heating, meaning the impact's effects were amplified. This reveals the nonlinear interplay between external impacts and internal activity, showing how a body already near instability reacts far more dramatically. In broader astrophysical terms, this event turns 3I Atlas into a natural collision laboratory for studying interstellar small bodies. From Oumuamua Enigma to 2I/Borisov's comet-like behavior, 3I Atlas now adds a third chapter, one that demonstrates how impacts can reshape interstellar travelers. The findings imply that many galactic comets may arrive as fractured survivors, eroded by collisions with dust, micrometeoroids, or rogue rocks, leaving us with a biased sample of the most durable remnants. The event also highlights the unprecedented capability of JWST to capture dynamic phenomena, combining imaging, velocity measurements, and high-resolution spectroscopy to reveal not only gradual outgassing but sudden, violent disruptions. Further archival analysis might even trace the exact moment of impact and the expansion of ejecta, offering a case study in high-cadence time-domain astronomy. Most intriguingly, this collision proves that the near environment of such objects is not inert. 3I Atlas likely passed through a region rich in particulate material, asteroidal debris, or micrometeoroids that left lasting scars. Some of its surface fractures, jets, or brightness variations may record a long history of cumulative impacts. Consequently, sudden activity in comets, whether flares, fragmentation, or dust bursts, may not always stem from internal stresses, but from external collisions. This realization deepens our understanding of comet outbursts and forces scientists to consider impact-driven triggers. As 3I Atlas continues its journey, the collision's aftermath may accelerate fracturing, destabilize its nucleus, and drive further mass loss. In the months ahead, it could undergo secondary fragmentation, intensified outgassing, or even partial disintegration under solar and tidal forces. To model its future, astronomers must now account for its altered mass, expanded surface area, and fundamentally changed thermal behavior, a vivid reminder that interstellar visitors are shaped as much by what strikes them as by where they come from. The collision likely altered the conductivity of the impacted region, invalidating earlier models that predicted smooth, uniform gas release. The resulting scar may have created new jets, shaded regions, or exposed volatile pockets that disrupt the comet's previous outgassing behavior. Observers should now look for asymmetries, subtle accelerations, or deviations in trajectory and brightness, as the impact could impart a small but measurable impulse, slightly modifying 3I Atlas's motion despite being minor compared to solar gravity and outgassing forces. On a broader cosmic scale, the detection of such an impact invites speculation about the perilous journeys of objects traveling between star systems. For millions or even billions of years, they traverse environments filled with particulate matter, micrometeoroids, and debris streams, each encounter posing a hazard. Repeated passages through molecular clouds or stellar debris disks could erode or destroy many before they ever reach another stellar neighborhood. The survivors we detect may represent only the most resilient remnants, those that endured the attrition of interstellar travel. Thus, this single collision becomes a key piece of evidence in understanding the lifespans, evolution, and detectability of interstellar objects. That 3I Atlas survived long enough to deliver this event testifies either to its intrinsic durability or to the rarity of significant collisions along its route. It imposes constraints. If such impacts were common, few bodies would arrive intact from their parent systems. At a deeper level, this event challenges the assumption that interstellar visitors are pristine relics carrying untouched records of their origins. Collisions act as cosmic sculptors, altering compositions, reshaping surfaces, and introducing internal stresses. When scientists analyze isotopic ratios, volatile abundances, or dust grain structures, they must now consider that impact alteration may have modified what was once a pristine signature. Consequently, divergence between 3I Atlas and solar system comets may not solely reflect differences in formation environments, but also their distinct collisional histories. For example, its high CO2 dominance might arise both from original chemistry and from resurfacing or selective erosion caused by impacts. Accounting for such effects becomes essential for refining chemical and dynamical models. Moreover, this collision provides a rare natural experiment for testing theories of small body strength. Most models of composition, density, and cohesion are based on solar system bodies observed directly or through crater studies, but now, an interstellar comet has offered a real-time demonstration. How does a dusty, volatile-rich body respond to impact stresses? How deeply do shockwaves travel? How much of the momentum is transferred to solid ejecta versus gas? These questions will refine our understanding of cometary fragmentation and disintegration. In the coming weeks, telescopes will track the expanding ejecta, map its kinematics, and monitor evolving chemistry, transforming this event into a landmark of interstellar research. JWST's detection marked only the beginning. As the illuminated ejecta expanded, curved arcs, filamentary tendrils, and shadowed regions emerged, shaped by solar wind and magnetic fields. Each structure revealed grain-size sorting, the mechanical separation of fine dust from larger aggregates driven by radiation pressure and gas drag. Over time, the evolving color and albedo of the dust will provide further insight, as freshly exposed grains appear brighter and bluer before darkening from solar irradiation and space weathering. JWST's mid-infrared instruments can detect thermal emissions from heated grains, capturing their cooling curves and constraining their size, heat capacity, and conductivity. Larger grains cool slowly, smaller ones rapidly radiate away energy. The thermal footprint thus becomes a fingerprint of grain properties. Beyond the dust, the impact opens a new window into the kinetics of gas-dust coupling. In a quiescent coma, gas entrains dust smoothly, but a sudden injection of energy disrupts this balance, causing larger grains to decouple and velocity stratification to emerge within the expanding plume. JWST's sensitive spectrometers can now dissect multiple velocity components, revealing fast and slow gas layers and their interactions. Meanwhile, ultraviolet photodissociation begins to fragment molecules into radicals such as CO, CN, and O, providing time-dependent chemical markers that differ from steady sublimation. Because this impact-driven outgassing occurred abruptly, the resulting transient chemistry offers a unique laboratory for non-equilibrium processes. If the collision struck an uneven surface or weak zone, it may have generated a non-radial ejecta plume, revealing asymmetries tied to the nucleus's spin, topography, and internal layering. Modeling the three-dimensional evolution of the debris could uncover the comet's rotation axis, its possible torque-induced spin changes, and even its internal structure. Finally, measuring the total mass and momentum of the ejecta compared to 3I Atlas's pre-impact trajectory provides a rare opportunity to quantify momentum transfer in a natural interstellar collision, an event that, in one instant, redefined our understanding of how such bodies evolve and survive across the vast reaches of space. The collision imparted a measurable impulse to the nucleus, propelling it slightly in the opposite direction. Though minute, this impulse could subtly modify 3I Atlas's long-term trajectory as it exits the solar system, introducing a faint but potentially detectable deviation. With precise astrometric tracking, astronomers may be able to disentangle this impact-driven perturbation from the ongoing non-gravitational accelerations produced by asymmetric outgassing. At a deeper level, the event probes the fracturing thresholds of icy, heterogeneous bodies. When shock waves propagate through a porous mixture of ice, dust, and voids, they can amplify along weak seams, reflect from density boundaries, or focus stress into localized zones of failure. The resulting damage, how deeply fractures penetrate, whether fragments detach or blocky chunks are expelled, reveals the internal architecture of flaws and grain boundaries within the nucleus. Should subsequent observations reveal secondary breakups or spreading cracks, the initial impact site could become the epicenter of ongoing structural collapse. Because 3I Atlas is interstellar, its material properties may differ markedly from those of solar system comets. Higher porosity or weaker mechanical strength might allow shock waves to travel farther or produce a finer, dustier ejecta cloud. Thus, the collision becomes an indirect test of how foreign mechanical compositions endure eons of cosmic ray exposure, micrometeoroid bombardment, and thermal cycling across interstellar space. Chemically, the impact may have liberated previously sealed materials, rare noble gases, deuterated species, or complex organics hidden beneath insulating crusts. Comparing pre- and post-collision spectra allows researchers to identify volatile species that were once concealed, revealing the primordial inventory of the comet's parent system and enabling comparisons to solar system analogs. Because the newly released gases have had minimal solar processing, they represent a pristine snapshot of interior composition. Moreover, the evolving plume provides a real-time experiment in diffusion and dispersion. Measuring how gas and dust densities decline with distance yields insight into mixing processes, interactions with solar wind, and how long ejecta remain coherent before dissipating. The slower this dispersion, the longer astronomers can study unaltered material and trace it back to source conditions. Understanding energy partitioning is equally vital. Determining how impact energy divides among heating, vaporization, sublimation, fracturing, and kinetic ejection helps refine physical models of collisions involving icy, porous bodies. From ejecta mass, velocity profiles, and thermal emission, scientists can infer the relative efficiencies of these processes, crucial data for calibrating small body impact physics. The detection itself marks a turning point in observational strategy. Now that a natural interstellar collision has been witnessed, astronomers are encouraged to adopt high-cadence monitoring for comets and interstellar visitors, seeking transient outbursts, anomalous brightening, or minor impacts. This event serves as proof that such phenomena are observable, not merely theoretical, and that coordinated, rapid response observations are essential. Multi-wavelength coverage, from radio to X-ray, will be key. Radio telescopes may detect synchrotron or free emission. Ultraviolet instruments can capture excited atomic and molecular lines, and optical telescopes can track scattering and color evolution. Together, these form a full temporal and spectral portrait of the event. As the ejecta interact with the solar wind, they may create localized microshocks or plasma disturbances, with charged dust and ionized gas twisting magnetic field lines, offering a rare opportunity to observe small-scale plasma dynamics in a cometary environment. Finally, the timing of the collision near perihelion is particularly intriguing. If the impact occurred just before closest approach to the Sun, the newly exposed material would have been subjected to maximum solar flux almost instantly, intensifying gas release and amplifying activity at precisely the moment of greatest thermal stress. The timing of the collision and the ensuing dust acceleration may have intensified asymmetric jets and rapidly altered thermal gradients within the nucleus. Observers would have witnessed a compound effect, a collision-driven eruption superimposed upon rising solar heating near perihelion. This synergistic coupling complicates modeling but yields deeper insights into the object's physical response. The event also raises intriguing possibilities regarding other undetected small bodies near 3I Atlas's path. The collision itself implies at least one fragment existed. There may be more. Follow-up observations could reveal faint debris trails or residual fragments trailing the comet, evidence of earlier collisions or shedding episodes. Mapping these could reconstruct the microdebris field through which the interstellar object traveled, potentially tracing it back to its origin, perhaps within a debris disk, asteroid belt, or planetesimal collision zone of its home system. If scientists detect differences in deceleration between the nucleus and ejecta, they could use this separation to estimate the comet's escape velocity, mass, and density, essentially reverse engineering the strength of its gravitational hold by observing which fragments remain bound. The complex post-collision morphology may also produce light echoes, where sunlight reflects off dust rings or shells at various distances and angles. Measuring the timing of these reflections allows astronomers to perform optical tomography, mapping the ejecta's three-dimensional geometry, densities, and velocities. Another subtle layer of analysis involves the coupling between dust and gas. In the immediate aftermath, gas expansion drives grains outward, but particle collisions and drag slow or fragment them, creating a miniature laboratory for studying dust-gas interactions under dense, dynamic conditions. Tracking how grains decelerate or break apart refines theories of dust loading and collisional coupling in cometary flows. Polarization studies offer yet another diagnostic tool. Freshly ejected grains may be smoother or more spherical than weathered ones, altering the polarization of scattered sunlight. Measuring polarization degree and angle across the plume reveal grain shape, alignment, and even rotation, with temporal changes tracing their evolution as the ejecta age. Because 3I Atlas is moving rapidly through the solar system, it's ejecta disperse anisotropically, leading-edge material piling up, while the trailing edge spreads more diffusely. This differential expansion may create density gradients or fallback zones where slower ejecta eventually return to the surface, modifying local albedo or producing transient dust coatings. From a broader perspective, this event cautions that by the time we detect most interstellar objects, they may already bear the scars of ancient collisions. Their once pristine interiors could be hidden beneath fractured, reworked outer shells, complicating efforts to interpret primordial chemical signatures. For future missions, especially those envisioning flybys or intercepts of interstellar comets, this realization is crucial. Understanding that such bodies may harbor structural damage, loose aggregates, or volatile ejecta clouds informs navigation strategies and spacecraft safety. The 3I Atlas collision thus becomes a vital case study in how fragile, reactive, and unpredictable interstellar bodies can be. Moreover, it serves as a high-energy analog for studying meteoroid impacts on smaller icy bodies within our solar system, offering fresh insight into crater formation, ejecta dynamics, and surface modification processes across diverse cosmic environments.